Welcome viewers. In this video we will see the DC transient response of RC circuit case 1 charging. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. DC transient response of RC circuit, resistance and capacitance, case 1 charging. Let us consider this resistor and capacitor connected in series. It is energized by the DC source E and controlled by the switch. By closing the switch, the voltage is applied. The Q0 is the initial charge available on the capacitor. I will see the description. Consider the RC series combination. A DC voltage is applied to the combination through the switch. Let Q0 is the initial charge on the capacitor. Initially the charge is available. So the initial voltage on the capacitor is V0 equal to Q0 divided by C. Right? Q equal to Vc. This is a formula, so that V equal to Q0 divided by C. V0 equal to Q0 divided by C, initial voltage. Right? Now we need to go for the time response. For that we need to apply the Kirchhoff's voltage law to this circuit. While applying Kirchhoff's voltage law, what is the equation? The applied voltage E equal to resistive drop plus capacitive drop. Voltage across the resistor plus voltage across the capacitor. That is E equal to I into R. The voltage drop is I into R. The voltage drop across capacitor is 1 by C integral I dt. So that is the KVL. Now we'll go for applying the Kirchhoff's voltage law for the given circuit, RC series circuit. At t seconds of closing the switch, apply KVL to the circuit, so that IR plus IC integral minus infinite to t I dt equal to E. So the applied voltage equal to resistive drop plus inductive drop. Right, I into R plus 1 by C. This minus infinite to t is split into two terms. Minus infinite to 0, 0 to t, I dt. Right. So this minus infinite to 0 is nothing but the initial voltage. That is V0. We already discussed. V0 equal to Q0 divided by C. Right. So this is the 0 to t is the after closing the switch. This is before closing the switch, initial state. So that voltage is V0. So that we can write this is equation number 2. The equation number 2 can be written as IR plus V0 plus 1 by C. This V0. This is the initial voltage. This term is replaced by V0. 1 by C integral 0 to t I dt, that is equal to E. 0 to t means after closing the switch. In the present case, let us assume that the initial charge on the capacitor is 0. Hence V0 equal to 0. Earlier we assumed that initial charge is Q0. Now at present we are assuming that there is no initial charge. So V0 is 0. So we can modify this equation. This V0 become 0. So substitute V0 equal to 0 in the equation number 3. So it become IR plus IC. This is IR, means I into R, resistance into current. 1 by C, 0 to dt, I dt equal to E. You can take, this is equation number 4. Now we can take the Laplace transform, so that the t domain can be converted into S domain. Again by taking inverse Laplace we will get the time response. Right. So I into R. R is constant. So integral of I, the Laplace transform of I is I of S. This is t domain. Now converted into S domain. 1 by C. So integral 0 to t I dt. That is by taking the Laplace transform of integral is nothing but I of S divided by S. Right. Differentiation means S into I of S. Integral means I of S divided by S. Differentiation multiplied, integration divided. The Laplace transform of E is E by S. Right. Now we taken the Laplace transform on both the side. This I of S is available commonly. Take outside. So is R is available here. Here 1 divided by C into S is available. That is equal to E by S. Right. Bring this term in the denominator on this left hand side, so that I of S equal to E divided by S already available. Then this term R plus 1 divided by CS. Right. Now we can go for the further simplification. Multiply S inside. So S into R plus 1 divided by C. So S got cancelled, 1 by C. Now take the R outside in order to bring the S plus A term. Then only we can take the inverse Laplace. So this R is taken outside. So S plus, here R term is not available. So it is divided, 1 divided by RC. Right. So finally we got this value I of S equal to E divided by R into S plus 1 by RC. Now we can take the inverse Laplace. Now taking inverse Laplace on both the side. So I of S become I of T. E by R is constant. 1 divided by S plus R 1 plus S plus 1 by RC is E power minus T by RC. So that is based on this value. 1 divided by S plus A equal to E of minus AT. Here A is nothing but 1 by RC. So that E power minus T by RC. Right. So finally we got I of T equal to E by R E power minus T by RC. So based on this value. Now this we'll analyze the equation. E by R is the initial value of the current directed by I. So RC is called a time constant denoted by lambda. Right. So E by R is the current, initial current, and RC is the called a time constant of RC circuit. Right. So that the charging current I of T is equal to this E by R is replaced by I. E power minus T divided by lambda. Right. RC is the time, RC is the lambda. Here 1 divided by RC is available. So minus T by lambda. So this is the final equation for the current. I of T equal to I E power minus T by lambda. Right. We will see the further analysis. This charging current seems to be exponentially decreasing from equation 6. Right. So E power minus this term normally reverse decreasing. When the time increases, the current is decreasing. The charging current is decreasing. The initial current equal to value of I when T equal to 0 is I. The steady state current value of I when T equal to infinite, that is equal to 0. Initially current and keep on decreasing and it become 0. I will see the further analysis. So the variation of the current with respect to time is graphically shown below. This is the time. When the time increases, the current is keep on decreases. That is the observation we got from the equation. Right. Initially it is I, then keep on decreasing. Similarly, we can analyze the voltage across the resistor and capacitor, ER and EC. Right. ER equal to R into I, V equal to IR. Right, I into R, that is equal to R into I is already we calculated, I E power minus T by lambda. R into I can be written as E. So E power minus T by lambda. So this is also decreasing in nature. Right, when the time increases, voltage across the resistor decreases. Right. In order to find the voltage across capacitor, ER plus EC equal to total voltage. So that EC equal to E minus ER. This term is brought this side. So E minus this ER is nothing but E into E power minus T by lambda. You take E outside. So that 1 minus E power minus T by lambda. This E power minus T is a decreasing term, but 1 minus, so it become increasing. So the voltage across the capacitor is increasing. From the equation we can easily understand. Right. This term is decreasing, but 1 minus is there, so that it is increasing. Right. Now we will see the graphical representation of this ER and EC. ER exponentially decreases from E to 0 as time increases from 0 to infinite. When the time increases from 0 to infinite, the voltage across the resistor is decreasing from E to 0. In case of the EC, the voltage across the capacitor, when the time increases from 0 to infinite, it increases from 0 to E. Both are different. E to 0 here, 0 to E. So that is given here. This is the time is available. The voltage across the resistor decreases from E to 0. Voltage across the capacitor increases from 0 to E. right? Graphically, the variation of ER and EC can be plotted as shown in the diagram. Now we'll see the time constant for the RC circuit. So the time constant lambda for the RC circuit, in equation 8, substitute lambda equal to t. The equation 8 is nothing but I equal to I e power minus t by lambda. Now we need to substitute lambda equal to t. So t got cancelled, e power minus 1. Otherwise 1 by e. So this value is 0.368 I. So what is this value? Thus the time constant for RC circuit is the time during which the current falls to 36.8%, because here the current is decreasing, right? So the time constant is time taken to fall the current to 36.8% of initial current. That is called a time constant. The current should decreases about this value, 36.8%. So in this video we discussed the TC transient response of RC circuit, resistor capacitor, charging, case 1 charging, discharging available in separate video. We analyze the current I of t, that is decreasing in nature. Then we analyze ER and EC also. ER is decreasing but EC is increasing. Finally we calculated the time constant also. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.